this set of lessons is going to discuss the inverse of a matrix. And so far we've talked about addition, subtraction, or the additive inverse, and multiplication of matrices. If you notice, we haven't talked about division, and that's because division with matrices is not defined. And instead we have what is known as the inverse of a matrix. So this is the multiplicative inverse, it's understood to be. So again, like I said, this is the multiplicative inverse versus the additive inverse, which we already talked about, which was very easy to find by just changing the signs of all the elements. The multiplicative inverse is a bit more involved. And so the definition says that if there is a matrix A, and then A inverse, we use that -1 exponent like we do with so many other things in algebra to define the inverse. This is the inverse, not the reciprocal, the inverse, and we know that A times A inverse equals the identity, and that A inverse times A also equals the identity. So again, these work in either way, we get back to that identity. Now, one thing to keep in mind when we're talking about inverses, again, we're only dealing with square matrices for these inverses. And the other thing to keep in mind is that if the determinant of any of these square matrices is 0, then it is not invertible. So it is possible that there is no inverse for some of these matrices. And if you need a refresher on determinants, then go back and watch the video online for that topic as well. We'll go over it a little bit when we talk about the 2x2 matrices. So I have two matrices here, and they look very similar, but they actually turn out to be inverses. So if we multiply A times B, if we multiply our first matrix 7, 5, 4, 3, by our second matrix 3, -5, -4, 7. Again, we go through, we got 7 times 3 is 21. I'm going to go a little faster with the multiplication here since we've had a little bit of practice with it. So 7 times 3 is 21, and then 5 and -4 is 20, and we do 21 minus 20 is 1. Then 7 times -5 is 35, 5 times 7 is 35, so we've got 0. 4 times 3 is 12, 3 times -4 is 12, so we've got 12 minus 12 is 0, and then 5 times -4, 4 times -5 is -20, and 3 times 7 is 21, so again we end up with 1. So that's good so far. Again, we need A times A inverse to be the identity. Now we have to check it the other way, B times A, so we've got 3, -5, -4, 7, and 7, 5, 4, 3. Again, if we go through, 3 times 7 is 21, -5 and 4 is 20, so we end up with that 1. 3 times 5 is 15, -5 and 3 is -15, so we've got 0. -4 times 7 is 28, 7 times 4 is +28, and then we've got -4 times 5 is -20, 7 times 3 is 21, so we have again the identity matrix. So in this case, these two are inverses. So that's really nice when we have the inverses, but how do we actually go about finding them? And like I said before, this is going to be helpful when we're actually trying to solve systems of equations, which is ultimately one of the major applications of matrices. So here is what we would do if we have a 2x2 matrix. Those are relatively straightforward, relatively small. First things first, we're going to interchange the elements of the diagonal. So if we go back up here, you can see that the 7 and 3 got switched here. Second step is we're going to change the sign of the other two elements. You can see here we had 4 and 5, and those signs just got switched, so we had the negatives. And then the last thing here is we're going to divide the resulting elements of all elements in the new matrix by the determinant. And I mentioned before that you want to make sure that you know how to find a determinant. In this case, I have it listed here. Determinant, if you have this matrix here is just going to be the diagonal A times D minus the other diagonal B times C. So pretty straightforward for a 2 by 2 matrix. So what the resulting matrix is, if we have A, the resulting inverse is going to be 1 over that determinant. Again, you're going to switch A and D, and you're going to change the signs on B and C. So take a second, make sure that everything looks fine there. So if we were to find the inverse here, again, first things first, let's find that determinant. So the determinant is going to be 2 times 4 minus 1 times 6, which is 2. So we are going to have 1/2, because 1 over our determinant. We're going to switch 2 and 4, and we're going to change the signs on the 6 and the 1. Last thing here, let's just distribute this. We are going to distribute the 1/2 to everything inside. So half of 4 is 2, half of -6 is -3, half of -1 is -1/2, and half of 2 is 1. So this is our inverse. We can check to make sure that this works. We multiply 2, 6, 1, 4 by our new inverse, 2, -3, -1/2, 1. So again, 2 times 2 is 4, 6 times -1/2 is 3, so we get 1. 2 times -3 is -6, 6 times 1 is 6, so that's 0. 1 times 2 is 2, 4 times -1/2 is -2, so that gives us 0, and 1 times -3 and 4 times 1 gives us our 1. And we could check it the other way as well. Again, writing the inverse first. Then times our original 2, 6, 1, 4. And we would see that we end up with the same matrix. So this is going to conclude this video. The next video is going to look at what we do when we have matrices of higher order than 2 by 2.